In this section, we'll be discussing horizontally launched projectiles. And with horizontally launched projectiles, we need to understand that we will be talking about things that are going 100% horizontally, following the x-axis at the point of launch. A few things about horizontally launched projectiles. The first thing is to talk about the direction of their motion. As this cannonball moves, in the beginning, it doesn't fall very much. It's hardly dropped at all at this point. But as it goes, the rate of drop becomes greater and greater and greater as it goes. And this is because of the different vectors that we were discussing earlier. We're applying vectors to this stuff. Let's get a nice arrow here. Initially, the velocity in the x direction is as such, but the velocity in the y direction is the tiniest arrow you can draw. Actually, if it's right at the cannon, if it was right here, there'd be no arrow. It would have zero initial velocity in the y direction. But as the cannonball moves, as it gets to maybe here, the velocities change, the vectors. Now, it's dropped a tiny bit. It's got the same x velocity though, that's the thing. And it's got a little more y velocity. And here's why. If you factor out air resistance, there's nothing to slow down the cannonball, because gravity's pull is 100% downward. So gravity has no horizontal effect on the cannonball. If you factor out air resistance, there's nothing that will slow down or speed up the cannonball, so its velocity will be constant. However, if you're talking about the vertical motion of your cannonball, there is an acceleration. The x velocity stays the same, the vertical increases. And as we go here, it drops more and more and more, because it is accelerating downward all the while it's moving at a constant rate forward. See how it's dropping more and more and more every time I draw it? I draw it here. Now it's going to have a very large. It's accelerating due to gravity. And this is why we did vectors in two directions initially, because you can see on the screen here we've got a number of vectors let out. Okay, let's look at a couple equations. So, we've got our old equations. These are ones we learned last time. Well, these three red equations are all to be used with the y-axis. So, for example, this one, height. The height of your fall is equal to 1/2 of the acceleration of gravity times the time squared. What this tells you here is if you know the height of it, you can figure out the time of the fall, or vice versa. If you know how long it fell for, you can figure out how high up it was. This one here is velocity final in the y direction. So we're talking about vertical velocity at a time. If you know it fell for 4 seconds, the velocity is 4 seconds times g. So just shy of 40 meters per second. Again, v final y again here, but if you know the height, only, you can tell how fast it's falling. Again, all three of these equations are vertical equations. This is your only x equation that we're going to work with here. Horizontal displacement is equal to velocity in the x, which is constant, times the time it fell for. Now, what's nifty is the fact that that time and that time and that time are all the exact same time. The one thing that ties projectiles together is time. Let's go back here real quick and do a little sample problem. If we know that the cannonball is launched at 10 meters per second, nice and easy, 10 meters per second, and we know that the cliff is 49.05 meters tall. If we know that data, we could predict where this cannonball will land. Let's just real quick take a peek back. We want to figure out something. We know the velocity and we know the height of the cliff. So, clear these things out. We know the velocity in the x direction, and we know the height of the cliff. And if we want to figure out where it lands, we want to figure out where it lands right here, delta x. What you're going to have to do there, to find where it lands, you're going to have to get time, because we don't have time. We want this. We need time. We don't have it. So what equation couples time with something else that's given? That one. So what we're going to do is we're going to say 49.05 meters is equal to half of g, which is conveniently 4.905, and you times t squared. So when we take 4.905 divided over, I believe 49.05 divided by 4.905 is going to come out to 10. And then we have to get the square root of 10. And when I square root 10, we see that that would then take 3.16 seconds to fall. So now we know that we have our time of 3.16 seconds. We know we have a velocity of 10 meters per second. Therefore, we can say that it went 31.6 meters horizontally. That's how you do it. A lot of the times, you're going to utilize this equation and this equation, and you just got to look at what you're given in the problem. So the homework that goes with this would be page 97, 1 through 4. And I think in a whole bunch of those problems, you are given y. Whoa, hello. You're given y, I think, and you're given x in a lot of those problems. So to be able to solve them, you'll need to probably use y to find time and use time with x that's given to find the velocity. I think that's what's asked in a lot of the problems.